Today is a kind of hybrid. We are learning AC circuits in class, but I decided to make this experiment here to motivate you and also give you some, how to say, connections to what we study in class with something that happens in our real world. Okay? So first, what we're doing, we are connecting a resistor. So if you are familiar with the resistors in the lab, this is a resistor. Okay? What's this? You go to any AC hardware, at least in Colorado, and you buy that to heat water. It's called bucket heat. Okay? I live in Colorado, 10,000 feet, it's very cold, and my water heaters are so big, so sometimes we do not have enough water for more than 2 baths. So I heat water because sometimes I like the bathtub. Okay? So I have a little bit of extra water with me. So I brought this from Colorado for today's class. Okay? So it says here that it gives you 1,000 watts, 120 volts. In AC, all the rating for AC is in RMS. What's the meaning of RMS? It's a value that we associate with the sinusoidal waveform. So the sinusoidal waveform is this one that we're learning with phasors. And RMS is an equivalent voltage that would give the same power in DC. So if you calculate, and it's not so difficult to calculate, you assume an equivalent voltage here. DC is constant. So in the same period, see, the same period, T, this DC voltage here should give you the same power. And how do we calculate the power? This is positive, this is negative. If I make the average, it will be 0, because the sinusoidal is symmetric. So it's 10 minus 10 times. He said, let's square. When it's square, it becomes positive. So you take the voltage square, and also the DC voltage square, and you make an integration from 0 to t divided by t, and take the square root of that. That's it. So that's the definition of RMS. Okay? We can give you more of math of this in class, but right now what matters is 120 volts RMS means that the peak voltage is 120 multiplied by square root of 2. So if you take the scope, we're not doing that because it's not very safe. I could do it with another thing, another, I would say, complexity. But I could take the oscilloscope and measure the input, okay? I'm not gonna do that because the oscilloscope is also connected to the same grid that I'm going to connect this. I don't know how is the isolation. I damaged oscilloscopes in my life, so I know how to damage an oscilloscope. So the best way when you measure something that's connected to the grid is to have an isolation transformer, and the oscilloscope is floating, is not connected to the same grid. But this is a more complex. What we're gonna do is we're gonna use the oscilloscope and only measure the secondary of the transformer. Transformer is something new for you, or most of you, or all of you, I don't know. But I start last class. A transformer, you step down the voltage by the turns ratio. So I made a little note here. The primary side divided by the secondary side is proportional to the number of turns on the primary side to the number of turns on the secondary side. So V primary divided by V secondary is N1 divided by N2. How do I know the number of turns? You don't know, because the manufacturer made the transformer is here, and when you buy a transformer, it says 120 to something. In this case, it says 115 instead of 120, and then it says the secondary is 30. So I am expecting that this is going to be maybe a little more than 30 on the secondary, because the rating from the manufacturer is 115. Okay. But let's make an approximation. I will go from 120 to a 30. So I would say that N122 is 1 divided by 4. So this is 1 divided by 4. That's what I expect. V2, no, 4 divided by 1. Because V2 will be V1 divided by 4. But the power should be balanced. The voltage in the primary multiplied by the current in the primary should be same as the voltage in the secondary multiplied by the current in the secondary. So what happens is to make V1 I1 equal to V2 I2, then the turns ratio here will be V1 is for V2 as N1 is for N2 as I2 is for I1. Because then we have I1 multiplied by V1 is equal to I2 multiplied by V2. Okay? So this is the, how to say, the fundamental equation that we use in transformers all the time, and that's for an ideal transformer, because a real transformer has a little bit more complexities, because inside of the transformer we have an equivalent module, but we are not discussing that. For this course, what you have to learn is this. V1 is for V2, as N1 is for N2, as I2 is for I1, that's it, okay? No losses, no nothing inside, but a real transformer has losses, has other things that we study in energy conversion or in power system schools. Okay? That's what we call ideal transformer. And if you go to PSpice or Microcat, if you find the model for an ideal transformer, that's what you should do. I'm gonna place this here because it's could be water. Okay. So what we expect? We expect 1,000 watts for 115, isn't it? No, 120. The rating for that is 120. The rating for the transformer is 115. But let's say for 120 volts RMS, the power of this heater is 1,000 watts, and we know that RMS is equivalent to DC. How do you calculate power? Power would be voltage square divided by R. Okay? So what resistance do we expect from there? The resistance that we expect from that little gadget is R is 120 square. 120 square is 12 multiplied by 10 square. Why I'm doing that? Because I'm gonna make an approximation very quickly. 12 square is 144. 10 square is 10, 0, 0, no. 100. I'm making a mistake. 120 times 10. No, R. I'm making a mistake somewhere. Okay, 144, that's right. Okay. So what happens is, when you make this calculation, you have 14.4 ohms, that's what matters. Okay. So that's what we expect. I took the ohm meter and I measure is 14, okay? So let's turn on. So on the secondary, I will plug my heater. Of course, the heater was made for 120, so the voltage at the heater will be less, will be 30, okay? And then I will connect my primary here. And I hope that there's no explosion. Right. So it's on, it's live, okay? How can we start looking to voltage? The oscilloscope should be more familiar because I've been using oscilloscope. So I'm going to take the probe and I will connect initially. See, there's a center tap here. The center tap is the middle of the terminal. I will have the secondary from here to here. This is half, okay? We have 30 volts from here to here and 15 from here. So I measure initially from this center tap to here. I'm gonna do it. screws here are big, so it's difficult to grab, to really keep the probe there. I use that knob, it's finished. Get like an alligator cable. No, a cable, not a probe. An alligator
It's on the
one
right.
side, alligator on
Yeah.
the other side. But not a probe. Alligators, not bananas. This is banana. I will need alligator.
Where are those?
If you see an alligator and a banana, they are different. A banana you can eat. The alligator is gonna eat you. I think. Maybe not. Alligator is vegetarian. Okay. Maybe I don't need the alligator, but bring the alligator anyway. I'm gonna turn on again. And I should have the voltage there. And I press auto set, which is easier. Great, sine waves there. Okay. How do we measure? Well, it says here 48 volts peak to peak. Okay? Peak to peak, that means it's 24 peak. It says the reticulate is 10 volts per division, so I have 10, 20, a little more than 20. So when I look here, this is 0, and this is kind of the peak here is 24. Okay? So what you're gonna do now, just do in your notebook, take 120 square root of 2 and tell me 120 square root of 2 divided by 24. How much is that? How much? Tell me.
I got 7.07.
7.07, right? So from here to here is 7.07. But now I'm gonna measure both, okay? Because we're measuring from here to here, okay? I'm gonna measure both, but initially, I will do this. You have to be careful, I told you have to be careful with your ground, particularly when you work with things like this that are a little higher voltage. So do not use this ground and think what you're doing. I have a probe from center tap to here. Now I'm gonna measure with this probe the other side. What do you expect? Everything you do in your lab, and maybe even in your life, you have to have a certain expectation to compare. So I know there is a sine wave here, and if I take this probe and I'm gonna get, what do I expect? I know because I have done this in my past, so what do you guys think is gonna happen? I hear some good answers, but I need a little bit of certainty from you. So you're gonna get the same, different, smaller. Okay, so I'm gonna do it. Okay? You have to have some expectation. So now I'm going to connect to the other side. And the problem here is maybe I need the alligator cable. Because the alligator cable is gonna help me. Great. I'll turn off have the connections with the cables, and I use my probe here. So first one is the same. It's from the center tap to the terminal that's on the top, and we saw that we have a sine wave. Okay, that's it. Again, I'm going to connect. There. Now I will connect the other one to the lower side, the terminal on the bottom, and it's here. I didn't connect the ground, I'm using the same ground. And I do auto set here. So it's going to plot both. Take a look now and describe me what you see. What do you see? Go closer, take a look. You can come closer, you can walk around. What do you see in the scope?